And he is somebody exceptional. I love them all. Like he is just someone.
Okay. This is a different way of looking at the ions I handed out today. So if you like this organizational scheme better, download this and print it, or just keep the one that I handed you. Same information. Now, there's two sets of information on here. One is over here on the far right, it says covalent, and then under it says molecular. You'll see this, the non-ionic naming conventions, you'll see it as covalent or molecular. Your dry lab calls it molecular, and your textbook calls it molecular also, but it's commonly called covalent, non-ionic. Okay, the ionic one is split up into two parts, positive ions, negative ions. They go together, one of each. And there's a charge balance that's required. Okay, so let's talk again about an ion. Now, the definition of an ion is crucial to understand naming. Because unless you understand what an ion is, you can't name it. So what is an ion? Okay, an ion is made up of a positive or negatively charged molecule. Okay, if it's charged, that means, so therefore, the number of protons does not equal the number of electrons. There's an imbalance of positively charged particles and negatively charged particles. Hence, there's a net charge. So you have to treat an ionic particle or ionic molecule from the positive perspective and the negative perspective. Now, the question is, what are the charges? That's what you're going to be memorizing. I will publish a list, which is going to be a subset of this for you. And I memorize all this. I'm not big into memorization, but the rest of the department is. So I'm preparing you for the rest of the department. And it depends on your teacher how brutal they're going to be regarding memorizing these particles. They'll have short quizzes frequently, etc. Okay. So let's talk about the ionic character. Let's look at a very simple example of an ionic particle. Good old table salt. Okay, that's ionic. How do I know it's ionic? Ionic means it's always got two parts. It's got a positive part, which is listed first. Positive is better than negative, so that's why it goes first. And it's got a negative part. If it's not a positive and negative parts, it's not ionic. No exceptions. That's the good news, no exceptions. If there's two positives or two negatives, then it's molecular. So the first thing you check for is it's ionic. If the answer is no, then it's molecular and you use that convention. Now I'm going to cover the tricky one first. Most of the work on the dry lab is ionic related. There's one little section on molecular. Most of it's ionic. So I want to best prepare you for dry lab is to focus on the ionic today. Okay, so let's look up sodium and see what charge it is. Now, on this particular chart, it's on the left side. Left side is positive, right side is negative. All right, is sodium on the left? Sodium begins with S, so go down to the S's. Is sodium exists? Positive, yes. So in the charge, hay fever season, I played chess with my neighbor yesterday. And I don't know who was sneezing and itching their eyes more, him or me. Okay, so it's positive. Charge is positive. You can go positive or positive 1 or 1 positive or just like that. Those are all equivalent. Now back in, I was a junior in high school and took chemistry. I learned it this way. So I will, by habit, frequently use that notation. This is more popular now of the 3. But they're all positive 1. There's a handout before you sit down. Okay, what about chloride? Okay, let's look up chloride. Now, chloride is going to be on the right side. And there it is. It's called a simple ion or simple anion. So these are all anions. Okay, so chloride is there. And it's a charge of -1. Okay. So this is, yes, ionic. Again, why? It's got a positive ion, a cation, and a negative ion, an anion. Okay.
So when does it change like the +1 or the pot? When will we know if it's like +2 or +3 or negative?
Say +2.
Oh, it will say it.
Yeah.
Okay, so we're not supposed to know. I see that, but I'm like, when are we supposed to know it? Okay, it'll be given.
So we're supposed to, I think once it's become 1, they have. Okay.
You're gonna have to memorize a subset of them, and I'll publish what those are. Well, 1A is gonna want you to know all of them, so just FYI. Okay, so how do we name this sucker? Okay, all the naming has 2 parts. Two parts. Okay, so first we just find the name of Na, that's sodium. Sodium chloride. So the question is, if I give you a name, I'm going to say or ask you, what's the formula? That's where the math comes in. We have to have a net charge of 0. That means positives equal negatives. No exceptions. Positives equal negatives charge-wise. Okay, so what's the net positive charge in sodium chloride? +1. What's the net charge? Negative. -1. So what's our net charge on this as written? 0. Up, we're there. Okay, so the formula for sodium chloride is going to be Na, only one of them now, chloride. One of them. Now you can write it like this if you want. Most of the time, it's not there. So if it's not there, it's the same as 1. Okay, so that sounds pretty straightforward, right? Okay, now that is by far the most simple example, but it's crucial you understand this concept of having a net charge of 0, because that determines numbers of those charged particles. To get zero as a net charge. Okay. Let's do another example. Let's do, sodium again. Let's do sodium sulfate. Okay, sodium we already know is Na plus sulfate. Let's find sulfate on the right. Now you have to be careful with the anions because some of them are complex. Like chloride is really simple. Sulfate is not. Sulfate is on the left side. You go down and find sulfates right at the top.
Yeah.
Okay. One sulfur, four oxygens. Charge is -2. So what's the net charge as written? -1. It's not zero. So we have to change that. What are we going to change to make it net zero? Two what? Two positive ones or two sodiums. Okay. So our formula is going to be Na2SO4. Now, for those of you who like patterns, we are going to write this two ways. I'm going to put parentheses around the multi-atom anions, the SO4s, the SO3s, the SO2s, the HSO4s. Put parentheses around it. Because if we need more than one of them, parentheses are already there. Now, that's optional. If you want it, you just clarify things, okay? So all these over here that are multi-atomic, think parentheses. Now it adds, some clutter with parentheses in there, but it makes it very distinct. We know that this is +2, -2. Net charge 0.
That's
Hmm?
So the parentheses is great.
It's optional, just for clarity, that's all.
Oh.
Okay, does everyone see why we need two sodiums? Cool. Okay, so we'll continue this now. Let's look at a couple things on this chart. Notice the word acetate. That's a very common ion, but you can write it two ways. You can write it like this or this. If you count the C's, H's, and O's, they're the same. The top one is an organic way of writing it. The bottom one is an inorganic way of writing it. I'm an organic chemist, so I like the top one better than the bottom one. And there's a reason it connotes function, where the bottom one doesn't. And the reason for that is this guy here is the acidic part. So that is, if you throw an H in there, it's acetic acid. So organic acids are written with a COO in it. The salt of the acid, which is minus the H, and we haven't got to that in unit 3 yet, but an acid is defined as an H coming off It's called dissociation, comes off, and that defines it as an acid. So bottom line is, same with this over here. This is called formic acid. When a red ant stings you, that's what it's injecting into your wound. It's formic acid. Now, if you look up the Latin for ant, it's forma. Hence the name formic acid. Now, let me tell you a story about how that was named. There was a chemist, I don't know, 150, 200 years ago, and he had a son that was mischievous. He liked to do cruel things to insects. So one day his father caught him burning ants with a magnifying glass in a bucket. And of course, his dad got all mad at him. And his dad decided to analyze the chemicals being given off by the burning ants in the bucket. It was formic acid, hence the name ant acid, formic acid. That's where it gets its name from. But it was from a mischievous son. Anyway, so you'll see it written in two ways. Top one, bottom one. The one I like to use is the top one because, again, I'm organic chemist. Okay, there's another one that's got a couple names, and that's this guy over here, hydrogen carbonate or bicarbonate. You've probably heard of bicarbonate of soda. That's a really old name, probably back from the alchemy days, very old. And it's kind of a misnomer. The more correct way to say it is hydrogen carbonate. So this is a carbonate part up here. So it's hydrogen carbonate. But you'll frequently see, particularly in agricultural products and food products, bicarbonate of soda. So it's hydrogen CO3. But you'll see it both ways. Okay, and then I think there's one more. I guess that's the only one on here. Okay, anyway, so that's clarification. Another clarification on this is over here on the left, the cations. Now you'll notice some of them have multiple names. Some of them, not all of them. And I give on this chart the old name, and that old name is not taught in this department for some reason or other. If you look on a food label, you're not going to see, like, for example, if we're talking about chromium, say chromium sulfate, you're not going to see chromium 2 sulfate. You're going to see chromous sulfate, the old name. If you pick up a bag of fertilizer or pesticide, you're going to see the old names as well. That's why I like to give you both names. Chemistry departments like to use the simpler version. And I'm going to talk about what that means in a second here. They want to use a simpler version with the parentheses. I personally think you need to know both. That's why I put both on here. Okay. If you go to the store and want to buy root killer, that's copper sulfate or cupric sulfate. So if you went there and said, I want iron 3 sulfate, you're going to go, we don't have it. And they got root killer by the bags, which is cupric sulfate. So that's why it's nice to know both names. Lead, there's plumbus and plumbic. They differ in charge. Cupric and cuprous differ in charge. Okay, so let's do an example. Okay, so let's write the formula for this name. Now that's Roman numeral 2. You need to know the Roman numerals 1, 2, 3, 4, 5, and 6. 1, 2, 3 is I. 4 is IV, 5 is V, and VI is 6. And you need to know those when you're naming cations, because that denotes the charge. Okay, copper 2 is the same as copper plus 2. So the 2 here refers to that plus 2 charge. Now, if you look on your chart, cupric, what's the charge in cupric? Same thing. Now, in your dry lab today, you're not going to see any cuprics, you're going to see copper 2. And the 2 is nice because it tells you the charge. Where the us and the ick. Cuprous doesn't tell you charge. Cupric doesn't tell you charge. All it tells you is the us part has a lesser charge than the ick part. So there's less information given with the ick and the us's. The other one is very analytical. That's why the chemistry departments like to use that one rather than the other one. But unfortunately, the world doesn't always act like the chemistry departments. They want to use old stuff that everyone has seen before. Okay, so let's do copper sulfate. Let's do root killer. So that is copper 2 sulfate or cupric sulfate. All right, what's the charge on copper 2? Plus 2. What's the charge on sulfate? -2. So it's balance. Net charge 0. So writing the formula, we would write oops, wait a minute. And so it's a +2, -2, net charge 0. So it's fine the way it's written. Um, hmm. Let's do aluminum sulfate. So right away, I'm going to tell you it's ionic because aluminum, what's the charge in aluminum? +3. Sulfate we know is -2. Okay, what do we do now? Remember when we balanced equations, what do we do? We need a common denominator. Like we're adding fractions. What's that? 6. So these are going to be related to +6. So how many 3's are in 6? And how many 2's are in 6? So that's aluminum sulfate. Now, did you go like this? Now, this is what he was referring to, what I'm going to show you right now. It's the cross. What does cross mean? Sides are opposite, right? That's the cross. But the reason why the cross works is because of the common denominator concept. Okay. Now let me show you where it sort of doesn't work. Let's do let's do Okay, cupric sulfide. Yeah, I told you this, we're, +2, -2. We do the cross. So if you do the cross on everything, you get to a situation like this. Okay, don't use the cross in a situation like this. If you choose to use the cross, look for a lowest common denominator, an LCD. Is there one between copper, 2 coppers and 2 sulfurs? What's the common denominator there? Oh, I mean, the lowest common denominator, 2. So you take out a 2 and both of them will be CuS. That's the only tricky part using the cross. But you don't need to use the cross if the charges already are equal.
Okay.
Yeah.
I have a question. So for the first one that we did, we just subtracted 1. Get it even. So why do we have to do this way for this one, but subtract 1 for the other one?
You're not subtracting.
Or,
Which one was it? The sodium sulfate?
yeah, the one where we added 1.
Okay, so let's do that one again. Okay, so we're gonna do Na +1, SO4, -2.
Yeah, so I get that part. I understand. I just add 1 to equal it out. Why can't we
Let's do the cross now with that. So. Oops. So we come up with the same answer. Was that where you're going with this?
Yeah, I was just wondering if there were 2 different ways to do it. Can we do it this way to get the answer instead of doing the common denominator for 6?
It all comes out in the wash.
So would you use a common denominator? So for that one where we just kind of balanced it, would we generally use a common denominator to figure it out like we did for the last one? The aluminum sulfate. And making it a 6. Is that like the standard way of figuring out?
The book uses the cross.
Okay,
I like to use a cross, but explain why it works.
Okay.
Now I'm not sure what the next class you're gonna be taking where they do it. They may use the common denominator way, they use the cross, or use them both.
okay,
I want to expose you to both.
okay.
All right. So that's the essence of the ionic method, is you're balancing charge. And that dictates the numbers. Now I mentioned that on the anion side, there's some complex anions, multi-atomic. There's usually, because we live in an oxygen environment, you have a lot of oxygen variance. Oxygen misses with everything. When you want to go, uranium is a big deal in the news right now because of the war. Well, uranium doesn't come as uranium when you mine it. It's uranium oxide. When you go to find copper in the ground, it's copper oxide. It's never just copper. Iron oxide's called rust all over the place. So the oxides, those oxygens get embedded in everything. Everything. Not 100%, but a lot of things come as the oxides. Okay, so that's going to be a segue over to the molecular way of naming stuff. Are there any questions about this ionic part?
Well, one thing I was wondering, if you scroll down a little bit to I think it was cupric sulfide. I was wondering, you did the cross method, right? And so I'm thinking, let's see, yeah, it's at the very bottom there. To the very bottom. And you have, so the copper has a charge of +2, and then sulfide has a charge of -2. So I would think that the charges would just cancel each other out and you only want them.
That's exactly. it.
Yeah.
That's why if you're, without doing the cross, if it's already balanced, stop. But if you do the cross, like you're in this mode, cross, 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 what you end up with is 2 and 2. 1 for each one, exactly. That better? Okay, so let's look now. Now, the name of this chart is the common ion chart. What does the word common mean? Huh? Yeah, one you see all the time. Does that mean there are others? Yes, there are others that are not on this list that are fine legally. In your lab, you're going to find some ions that are not on this list. So how do you deal with it? Okay, so I'm going to show you an example of that before we go on to molecular. Okay, we've got V for vanadium and sulfate. We got 3 sulfates though. Let's look at the charge. What's the charge on 1 sulfate? What's the charge on 1 sulfate? -2. Times 3. That means we have a net charge in here of -6. So what must the vanadium be? We have 1 vanadium. What must the vanadium be to balance in this? 6. Look on your chart. You see a vanadium 6? Bottom left? No. But it's got to be a 6 because it's balanced. All right, let me show you up here then. Okay, this has 3 of them listed, which are the common versions of vanadium. And this again reflects charge. So if the 4 there reflects the charge, what must the charge be on the one I just wrote? Six. So it's going to be vanadium 6. Sulfate. Now, the reason why I don't put a 3 in the sulfate is because there's only 1 sulfate that exists. There's only 1 SO4 that exists. Only -2. Vanadium has a bunch of different charges. So even though vanadium 6 is not on the list, it's still a +6. And that balances out the 3 sulfates at -6. So you're going to see a couple of these on your dry lab. Okay, so let's go on to why am I running out of juice? I've got it plugged in, I don't understand. I don't have it plugged in. When you need juice, you gotta plug it in. All right, okay, so molecular or covalent. Now, again, most of the problems will be ionic naming. You'll have some acids you're gonna skip. And the molecular ones are gonna be very few. But you still need to know how to do them though. So let's come up with an example. Let's do a hard one. Let's do H2O. Now, normally we have oxygen is going to be -2. And is H a positive ion? No, normally it's a negative ion called hydride, one of the simpler anions. So that reason, -1, -2 is not ionic because you only have one of each. So that means we have to go over to the molecular way of naming things. That's where this chart comes in up here. Mono, di, tri, tetra, penta, etc. That's how we tell how many there are. So, how many hydrogens do we have? Again, this is in 2 parts. So, it's hydrogen off the periodic table. And over here is a ide. So, what's oxygen? Oxide. Okay, how many hydrogens do we have? That's dihydrogen monoxide. Now notice the 2 O's together. So we're going to take out one of them so it reads better. So dihydrogen monoxide is called water. What's nice about this name is water in every language is usually different. You know, Spanish is agua, agua depends on how you pronounce it. In English speaking, it's water. But it's always dihydrogen monoxide in Spain, in France, in Russia, in Iran, maybe in the United States. So the scientific name is constant. It's international in scope. That was one of the problems with the alchemists, is they didn't have names that were universal like we do now. Okay, so H2O is dihydrogen, 2 hydrogens, monoxide, monoxide. Now this is always an ide on the right. And the one on the left is what it says on the periodic table. Yeah,
So you said the hydrogen.
it's -2.
Oh, sure.
Hydrogen is +1 and also -1. It's +1 when we're dealing with acids only. Otherwise, it's a -1 hydride. Good question. Okay, so let's do another one here. Okay, let's name this guy. 2 parts. So is this ionic? Okay, Cl is a -1 and O is a -2. So it's definitely not ionic. That means it's molecular or covalent. So chlorine from the periodic table and we have oxide as the ide. So we have 2 chlorines and 3 oxides. So it's dichlorine trioxide. Very, very straightforward compared to the ionic ones. Ionic is straightforward most of the time too, but it can be. All right, so that's what I wanted to cover today. That's what we're doing on our dry lab. Any questions about the molecular way of naming things? Now, your dry lab goes into one little detail that I covered, but I want to make sure you understand it. The cations can be in different formats. And you have 2 subunits. One subunit deals with the cations that don't have different forms, and the next one below it goes into the ones where it has multiple forms. And they kind of explain it in a kind of non-straightforward way. And I don't know why they do that. I didn't write the. So, okay. Any questions?
Like, I just wanted to.
May 1. I'm just gonna keep it that way because everyone's been looking at it. I thought it was sooner than that, but I'm only gonna say.
Are we gonna have a chance to go over unit 1 and 2?
We don't need to.
Yeah.
Because everything in unit 1 they're using every day. That's why we spent so much time in unit 1, so you're prepared for unit